Okay, so 2 presentations in a row here. Now it's going to be about the Xen Hypervisor and how we're progressing on the safety certification of it. So I was supposed to give this talk with Stefano, but Stefano couldn't come, unfortunately, so I'm going to do it on his behalf. Okay, so the Xen Hypervisor. So it's an open source project. I'm going to go a little bit quickly because I've got super many slides. It supports a variety of architectures. In our case, we're using it mainly on x86 and ARM, but there are others. And you know, it's a quite healthy open source community with multiple vendors contributing and so on. Okay, so let's look at the architecture, a modern Xen architecture. We've got the Xen Hypervisor at the bottom. And it's providing either by, let's say, some sort of small emulation, but in the ARM case, it's actually more virtualization of devices in hardware. So there's the basic stuff, just the minimum you need to run, I guess, which is timers, an interrupt controller. There's a driver for our IMMU. You're essentially virtualizing an MMU for the guest by using the 2-stage translation. Sometimes you have PCI controllers that you virtualize, and so on. On top of that, we run the domains. There's typically a privileged domain that we call DOM0, which by default owns all the devices. So it has the device drivers by default for all of the hardware. Now, the DOM0 also has a Xen-specific tool stack. That makes it easy for you to dynamically create guests. Right, and now you can, if you need, sort of assign a device to a DOM-U, which is not privileged by default. But the default is that all the hardware will be assigned to DOM0. Okay, so DOM-Us are unprivileged. They only get devices that are specifically assigned. And you can use some sort of, let's say, paravirtualization to share devices between multiple DOM-Us. And the backends will then typically live in DOM0. So this paravirtualization can be Virtio or the Xen PV. Okay, now, this is what I've just shown here is what it looks like for ARM and largely for RISC-V. Now, if we look at the x86, you'll see that they look very similar today. So if we're using the PVH mode on x86, it's essentially the same. So we've aligned the architectures very much. It didn't used to be this way. For x86, there was tons of emulation done in QEMU. But now you can run DOM-Us without QEMU. You would only use QEMU if you want to do paravirtualization. So that's nice. Okay, so with the mechanisms I described a moment ago, we think we can cover, use cases all the way from infotainment down to more safety-critical use cases. And here we're talking about high complexity on the left to lower complexity on the right, not referring to the application or the VM payload. We're just referring to the hypervisor configuration. So on the left side, we tend to have much more device sharing. So there's more paravirtualization, backends, front ends, some device pass-through, so on. Whereas on the right-hand side, we do more real-time. It's more static partitioning, and so on. And it's not black and white. There are grayscales. It's a whole spectrum here in between. And we think Xen serves us very well here. Okay, so this is a variation of the image I showed in my previous talk. So we've got all kinds of workloads here. And as you can see, Xen is running on all cores. And therefore, the Xen abstraction layer is applied to all these systems. And we've got complex systems on the left to, let's say, more simple static setups on the right. Okay, so how do we do static partitioning? One of the things that was added a while back ago was the null scheduler. So it It's really a scheduler that does nothing. In fact, if once, when you're setting up the VMs, it'll automatically allocate each vCPU to a physical core, and if you try to over-allocate, it's going to fail. So, the good thing with it is that when Xen runs the schedule function, it really does nothing. Whereas this credit scheduler, it's nice. You can overcommit. You can have multiple vCPUs on a single physical core. But even if you set it up one-to-one, it's still going to look into some data structures to do some scheduling. So it's going to add a little bit of latency. Okay, so the null scheduler ends up with a one-to-one mapping. Another thing we've got is what's referred to DOM0less, and we're calling it DOM0less boot here. So historically, when you started system running Xen, you would load Xen, the hypervisor itself. You would point it to the images for DOM0. DOM0 kernel will boot. You would use the Xen tools to dynamically launch new guests, and that's how you would start up. Now, the secondary guests that DOM use, they wouldn't start up until DOM0 was fully booted and you could start running these tools. So that was not great. So we added DOM0less boot, where essentially now you can tell Xen to start all the VMs in parallel. So this dramatically decreases the boot time for the DOM use. Also, it makes DOM0 optional. So if you think about a system where you've got only static partitioning and device pass-through, there's no device sharing, you could get rid of DOM0. Okay, so that's what just explained. Another feature that's interesting for the static partitioning case is cache coloring. So, if you think that we're running, let's say we run 4 guests and you got one of the guests going crazy and doing all kinds of mem copies all the time, and it's going to start thrashing the cache, the L2 cache. So even if you've got, one-to-one mappings on the cores, you still have interference being caused by other potentially malicious guests, let's say. So cache coloring is a scheme where you essentially, what you do is you exploit the architecture of the L2 cache, and you find out how many ways it has into the banks, and you allocate your memory for each guest in a fragmented way, such that all memory for any given guest will always pick the same way in the cache. This will, of course, limit the amount of guests you can launch with these properties. But if I remember correctly, on our architecture, we've got 16, which is enough for most of the static partitioning cases. There's a lot of details here. I'm a little short on time, so I cannot cover it. But we can talk, if you want to talk more about it offline, we can. We've done some measurements on the interrupt latency, and this thing really works. So you can see, if you look at the Xen with interference, which is the 5th entry at the bottom, you can see how the latency just starts going up. Whereas Xen with cache coloring and interference, you keep the latency down. Okay, here's an example of the more infotainment with more complex Xen setup. I think the main difference here is we've got a lot of device sharing, a lot of Virtio, and some PV drivers at the bottom. But even for this use case, we still want to use DOM0less boots to lower the boot times. Okay. So AMD is working on trying to safety certify the Xen hypervisor. We're doing it in a way that it's called what's called the safety element out of context certification, where we're trying to certify the source code of Xen. So it's not a specific build. We're aiming for SIL 3 and ASIL D, which are the highest in the automotive space. I think in the SIL area, there's actually SIL 4, but as far as I know, it's very rarely used, maybe for nuclear plants and things like that. So the way we're certifying and doing the documentation with, I'll come more to that, but the way we do the architectural specs and the requirements and the testing, it's based on how the upstream community works. So, trying to make so few changes as possible to the workflows, and in collaboration with the upstream community. And we're doing it for x86 and ARM. So there's going to be 2 configurations of Xen that we're targeting. It's not for any specific board, it's the configuration. Remember, we're doing source code. So we're going to describe the assumptions of use, which are essentially the interfaces. And any platform that can fulfill those requirements would essentially be supported. We're not doing it on a private fork, so to say, so anything that we target that's in scope for our safety certification, we are trying to upstream. Now, we do also, as everyone else has schedules and timelines. We need to put some sort of deadline. But our goal is to upstream everything. If it's not upstream by the time we need to freeze our code, we're going to take whatever version is under discussion with upstream. But as far as I know, almost everything has been posted and is under discussion. For example, we had a discussion with Bertrand yesterday about Virtio PCI, so that's going to change a little bit. And there are things, that we're under discussion. But it's not a fork that we're intent to keep forked forever. It's more like a staging tree, so to say. And we are open to collaborate with other vendors. Okay, so for the safety certification, we had to slightly modify the Xen architecture that I described at the beginning. So what traditionally is DOM0, we've now split into 2, because DOM0 has, it has both the privilege side of it. It can sort of reboot the machine. It has other privileged operations it can do. And traditionally, it also had access to all devices. But we want to support a model where we want to do Virtio and paravirtualization and have the backends run in a domain that does not have the power to reset the machine. So we split DOM0 into what we call the control domain and a hardware domain. Okay, so I'll start with the control domain. The control domain is privileged. It can do anything it wants, basically. But we don't really intend for it to have any device drivers. So it's going to be more like a monitoring domain, and you can request to it to reboot the system if you need to, things like that. And we expect this to be running a safe workload, a safety-certified workload. Now, the hardware domain will have some privileges, but they're very limited. So it will essentially just have enough to implement a Virtio backend or a PV backend. So the DMOps, it will be able to map memory of DOM-U, but only selected DOM-Us. Right? So it's not any DOM-U. You have to configure which DOM-Us it can map. It will own all the hardware by default, but as I said before, you can reconfigure that to assign hardware to other DOM-Us. And then we have the DOM-Us, which are completely unprivileged. They can have device drivers only for assigned hardware, and they will run the paravirtual front ends, the drivers. Okay, so there's another split you can further do here. The hardware domain, you can take out that and split and have multiple of them, so you can have specific driver domains that essentially you don't need to bundle all the hardware into one domain, because let's say you have a device driver that has some error and sometimes bugs out. Maybe you want to run that in a separate VM than whatever other This is still on the QM software, let's say, the non-certified. Right. On the left-hand side here, the green domains, they're all safety certified. We don't think it's a good idea to run paravirtualization between a safety certified domain and a non-safety certified domain, so to say. So those are separate. Okay, I'm gonna jump this stuff. So yeah, I just explained that for Virtio. We are looking into ways to do, so with Virtio, as we discussed in the previous sessions and all morning, there's a problem with how Virtio works on Xen, that since all the transports today are based on trap and emulation, and the trapping and emulation in Xen will, while the emulation is happening, the vCPUs are essentially waiting. And that's not good for real time, and it's not good for safety applications. So we need to get rid of that. I think the long-term solution is really Virtio message end-to-end between the driver and the backend. But we're looking for intermediate ways to do that too, since many of the guests today are not yet Virtio message capable. Okay, so as I said before, we're targeting ACLD and CL3. And in phase 1, we were looking to do the safety concept review with our assessor. And that was completed and successful in November last year. So that was a good milestone for us. There's still lots of work to do, but it's progressing. We have done a lot of progress on the upstream side. So for example, on the MISRA C compliance, all the rules that are going to be part of this have been accepted upstream. There are still a few violations, but as I heard a couple of days ago, expect to get those out of the way within a couple of weeks. So essentially done on the MISRA C side. Let's say all the controversial stuff is done. We are ongoing with the new architecture, so, with the new roles, I mean. We are writing a lot of documentation internally and tests, so the ARC specs, the requirements, the test specifications, and so on. There is also, let's see, I've got the, right. So when we safety certify Xen, we need to have traceability all the way back and forth, all the way here between test cases, test results, and all the way back to market requirements. And this has to be documented in a way that we can essentially generate a report with this traceability. And this is not something that open source projects typically do. So there is a tool called OpenFastTrace, if I remember correctly. Yes, yeah, I think it's, and it's a very lightweight tool. So the idea here is that we're going to write just text files, like MD files or markdown files. And by adding tags to these files, we can cross-link them. So there's going to be an architecture file that has special tags that refer to the requirements file and so on. Now, these files are going to be treated as just text files in the repo. So we can use the normal flows to review them. It's just git send email to send patches. And so it's a lightweight change to the development flows or workflows. Here's an example of what the text file looks like, and the reports. Right, so we're using OpenFastTrace. It's a very mature tool. It's been used by other projects before, so many examples here. Right. So here's the Virtio across clusters that I talked about on the last talk. So that's going to be important for the automotive stuff. So remember, this is mostly done on the QM side of things. Yeah. So I think I am done now, actually, just in time. So we got a few minutes for questions.
So congratulations on the 2024 milestone.
Okay, thanks.
The obvious question is, what do you think the timeline is for the final?
Ooh, that I don't actually know.
Is it a 2026 thing or not
Let me
this
get
year?
back to you on that.
Okay.
Yes?
Has there been much progress on getting Open Fast Trace to export SPDX and import it so we can start to put the system together?
Nice. Thanks.
Has there been? I haven't heard much about, I haven't heard any updates from the Open Fast Trace side of SPDX generation and consumption. Do you know?
No, I don't know.
Okay.
Okay, so if I got it correctly, all the safety-related artifacts would be public, right? And embedded in the Xen repo.
So it's not all of them. So
Not all of them.
it's the documentation. And so all you need, all the documentation. But the actual test cases, I don't think will be. So those are going to be part of the AMD package. Yeah, I'm a little unsure how those are going to get distributed. But I think, there's going to be some sort of commercial aspect to that.
Okay, but I guess the details cannot be disclosed now.
I don't know the details of the. I don't think everything has been
Okay, thank you.
decided yet.
So it was mentioned in this talk and also in a previous one that there is a concern about trapping into the hypervisor when writing to MMI or.
Yes.
I was wondering if that could be solved by setting up an SLA or saying, okay, this trap will never take more, from a safety perspective, will never take more than X microseconds, X milliseconds.
Yes. So actually, one of the things we were exploring is to do exactly that. But to achieve that, you need to sort of modify a little bit the Virtio specs. So for example, in Virtio PCI, when you do a write to configuration or read from configuration, you expect to get the answer immediately from that load, let's say, right? And that load may take an indefinite amount of time to emulate. We could, of course, bound the time. You say the implementation must do it. But you could also decouple this. If you change the Virtio's protocols a little bit, you could make them asynchronous. So you do, okay, I want to read the configuration. Tell me, I can pull a register until it's done, right? I don't need to get the answer in that same instruction. That's what's causing the problem. You see what I mean?
Yeah.
Yeah.
Thanks.
Yeah.
So the IOREC implementation is problematic because you need to give back an answer straight away. And you could say if the answer for read register is not available, I will answer 0. Problem is none of the driver on the other side are expecting that on a 0, you will have to retry again.
Mm-hmm.
So you will have to change the protocol. Also, it's a bit going against the philosophy of Virtio because Virtio does not say that you are speaking to a software emulated side. Virtio is made so that you can make a Virtio hardware implementation. Nobody expects that when you read a register, you don't get the answer. You either get the answer or you trap because there is a bus exception or etc. Which means we could circumvent a little bit those kind of stuff, but that means we would open a completely new way to handle IOs, which is not a good idea. And that's why Virtio message comes in a way, because we say, okay, we don't do IOs anymore. We send a message, and at some point, the answer will come. A little bit that you do that over network. And then the driver on the other side can expect that it will not get an answer. And it can wait in another way, but you don't need to freeze it. And the hypervisor, you can create an isolation. The ultimate on the safety side, what we are discussing now is, okay, what would you need to do so that a front end can be safety certified when the back end is not? And that was not possible before. Now, when you have Virtio message, you could say, okay, but the front end, if it expects an answer in 10 milliseconds and does not get it, it can still handle it. So from the safety point of view, you created a barrier where you have a dependency from the feature point of view, but you don't have a dependency from the code point of view. And this is opening new ways to do things in a standard way. There was ways to do that before, which was build up your own protocol and do it completely differently. But now we have a standard way to do it. So in the future, we expect that it will be possible to say, I have a backend which is network backend that I use to send log messages. I have a safety application which sends logs messages sometime, but the log messages themselves are not safety related. That's debugging or etc. So if I send a message and it's not sent, whatever, I'm still safe. I don't go against my safety assumptions. But I still use a driver which is not safe, which is kind of problematic at the moment where you have to go up layers when you do that usually in safety. But the IO workaround is not good.
Yeah, well, I mean, your choices there, as Bertram said, is either return 0, which would be unexpected, or declare a bus error, emulate a bus error into the guest, which is, you know, don't trust the OS to handle that gracefully. So probably your only choice there is to shut down and restart, right? So, I mean, you could write a safe OS that handled bus errors and correlated them well and things like that, but yeah.
I was thinking more in the lens of the whole Virtio device to be part of the safety specification, so you can guarantee that it will always always have a certain SLAs.
Absolutely. If you can, well, some hypervisors put the devices in the hypervisor, and then when they do their safety certification, all of that is safety certified, right? A complicated device like a GPU, well, first off, the GPU itself is very hard to safety certify, and then the driver for I think it's useful to be able to draw that line, as Bertram had talked about.
There is a model definitely where if your backend has a safety certification level upper than your front end, then you can use IORAC because you don't care, right? The safe part is the backend. So, yeah, and we are doing that. For example, having Zephyr as a backend is kind of a good use case that we have right now. We have also the case that I presented with FFA where it's not a safety requirement, that's a security requirement, but your backend is in the secure area. Which means if the backend is going crazy, well, that's not really a problem because secure world going crazy just means that if you are lucky you have a watchdog, you will reboot. But you cannot restart anything in the secure world. You cannot recover from an error in the secure world. If an exception is happening, that's dead.
I mean, if you take the example, let's say you have a real-time guest, single core, right? And occasionally it's doing a Virtio load. That's gonna go away, and you don't know how long time. So your interrupt latency is gonna.
It's the real-time bubble.
Right, it's the real-time problem.
You're not in control. You can't process another interrupt while you're waiting to do that, right? Your virtual CPU is stolen for this load or store.
Are we on time? Are we? Okay. I guess we're done. Thank you very much.